All right, so today I'm joined by my TA Indiana for this fluid mechanics buoyancy video. Buoyancy is a force, so buoyancy problems are force problems that require free body diagrams. So this video is going to start off with a super quick mini lecture about Archimedes Principle so you understand how to find a buoyant force. And your TA Indy is going to help us out with a free body diagram for this object which is floating at the interface between two fluids. And good news, two liquids instead of just one doesn't really make it all that much more difficult. So Archimedes' principle states that the buoyant force acting on a floating or submerged object is equal to the weight of the fluid that it displaces. Oftentimes, this will be calculated using the specific weight of that fluid times the amount of volume that is displaced. Or if you want to work with density instead, it's rho GV, density times gravity times volume. And just note that a lot of times volume is written in fluid mechanics textbooks with a line drawn across the middle. There's nothing that special, it just helps distinguish it from V, which is also used for velocity. So to help understand buoyant force, let's consider a completely submerged cube. Pressure from the fluid is going to exert itself on every side of this cube, left, right, top, bottom, front, and back. The left and right forces will cancel each other. They're completely symmetrical. Same with the front and back. But the top and bottom forces actually will not cancel each other out. That's because the pressure acting on the top surface is different than the pressure acting on the bottom surface. If you remember from the hydrostatic equation, pressure in a liquid increases as you get deeper because it's carrying the weight of all the fluid up above it. So the upward force due to pressure pushing up on the bottom of this box would be stronger than the downward force of the pressure of the water on the top of the box. And this small difference in forces due to the small difference in pressure may help you understand why a buoyancy force exists at all, because there's more upward pressure at the deeper depth pushing up on the bottom surface of a submerged or floating object. It's not going to be essential for this problem, but the line of action of the buoyancy force is going to pass through the centroid of the submerged or floating object. We'll come back to that in a different video when we talk about stability of floating object. And stability is mainly used for boats, where if a boat starts to tip over due to wind or waves, will it right itself or continue to tip all the way over, stable versus unstable? One last thought example to help understand Archimedes' principle. Let's talk about an anchor and the difference in how the buoyancy force acts when this anchor is submerged on the bottom of the ocean versus being carried in a boat. When an anchor is down on the bottom of the ocean, it displaces an amount of water only equal to its own volume. And since anchors are really dense and heavy, this is a very small amount of water. And so this is why it sinks, because gravity force pulling down is much stronger than this very small buoyant force due to the very small amount of water that's displaced. But when this same anchor is raised up and hoisted into a boat, now the anchor is floating, which means that the buoyancy force has to be much larger in order to offset the gravitational force pulling downwards, which means that the amount of water displaced will be much larger. So the anchor displaced a very small amount of water when it was submerged, based on its own volume. And a floating object will displace an amount of water equal to its mass so that the buoyancy force and the weight force both cancel each other out and the object floats. All right, so let's take a look at this example problem where we have a wooden block that is floating at the interface between two liquids, water on the bottom and oil on the top. To make the math easier, we'll make this a gigantic cube of 1 meter on each side, and we'll say that the system is at 20 degrees Celsius. Now the temperature is important because it's going to affect the density of the liquids. You can look up in a table and find the density of water at 20 degrees Celsius is about 998 kilograms per meters cubed. And so what we're trying to find in this problem is what is the density of this cube, or what is its specific gravity, if we know that it's floating 0.3 meters in the water and 0.7 meters in the oil. There are many kinds of oil with widely varying specific gravities, so we'll arbitrarily pick a kitchen experiment and call this olive oil, and look that up in a table and find a specific gravity of about 0.915. Said before, I'll say again, every buoyancy problem is a force problem, and every force problem requires a free body diagram. So free body diagram for this cube has the weight vector pointing down, and two buoyancy forces pointing upwards, one for the displaced water, one for the displaced olive oil. Write out the equilibrium equation as sum of forces in the y direction equals 0. Got the weight vector is negative because it's pointing down, and the two buoyancy vectors positive, they're pointing upwards. We use the version of the buoyancy force that is rho vg, density times volume times gravity. And the weight vector for the cube, mg, I'll also add a density term into that because that's the final answer that we're looking for. Nice thing for this problem, there's a g in every term, so I can just cross off the 9.81s, don't even need to include it. So put in the density of water, 998.2 kilogram per meters cubed. The volume of water displaced is going to be the cross section of the box, 1 meter by 1 meter, times 0.3 meters, the depth of just the water. Not the entire cube, only the part of the cube that's displacing the water. For the olive oil, density of the olive oil is specific gravity of the oil times density of water. That's what specific gravity is. It's a multiplication factor to take the density of water larger or smaller based on whether it's more or less dense than water. So 0.915 specific gravity times density of water, 998.2. And the volume of the oil displaced is the 1 meter by 1 meter top cross section of the box times the depth of oil, which is 0.7 meters. And a little bit of algebra, and that gets to a density of the cube, 938.8 kilogram per meters cubed. And if we wanted specific gravity, we can divide that number by the density of water, 998.2, and get 0.9405 as the unitless specific gravity. So to double check whether this answer even makes sense, we can compare this final answer to the densities of the two fluids. Since the object is sitting on top of the water, it needs to have a density less than water, so its specific gravity should be less than 1, which it does, so that makes sense. But this object is not floating on top of the oil. If the cube had a specific gravity of, say, 0.8, it would actually be floating on top of the oil, touching the air. So we expect the cube to have a specific gravity greater than 0.915, which is specific gravity of the oil. Final answer between 0.915 and 1, between the specific gravities of oil and water, that is the range of possible values for this scenario. A specific gravity greater than 1 for the cube would make it sink down even below the water, and a specific gravity less than 0.915 would have it floating on top of the oil. The only way to get it right at the interface is to be between their two values. And you can even tell based on the fact that it's sitting higher in the water, sitting more inside the oil, the specific gravity should be closer to the value of the oil than it is to the water, which again helps make sure that this answer does seem to make sense, since the 0.94 is closer to the 0.91 than specific gravity of 1 for the water. In this problem, all the volumes were very boxy and very easy. This next video is going to show you an example of a cork that gets wider as it gets higher, and you'll need to calculate how low it sits in the water, which is like calculating the draft of a ship. Same free body diagram, same forces, but the math is more complicated because of the more complicated shape, which gets you a little bit closer to reality because the bottoms of ships are normally very strange shapes.